Okay, so notes 1-4, we're going to be verifying inverses. So at the top it says there are two ways to determine if two functions are inverses, graphically and algebraically. So there's two different ways that we can determine if they're inverses or not. So the first couple of examples we're going to determine graphically. So if you look at number 1, we're given a graph, we're given two different lines, or in this case, rays, and we're determining if they're inverses or not. So remember, we've been talking about if you're given a graph, or you have a graph and you want to find the inverse, you're just flipping the points. So that's one way of determining if these two are inverses of each other. So you can look at, just say this point here, that's -1, 1. So if we were to reflect that over y equals x, that would become 1, -1. So notice 1, -1 is this point here. So that reflects. You can check the other points also. And something we haven't gone over on a graph, if they intersect, so I'm going to go ahead and write this down. So if they cross or intersect, they must cross on your intersection line, which is y equals x. So notice on this one, they are intersecting, and it's at that point there, which is on the intersection line, which is y equals x. So that's also something you need to check for. So if they intersect, they don't have to intersect, but if they do, it has to be on your reflection line. So these two would be inverses. You can check all the points. It's reflected over that line y equals x because they're just flipped. Okay, let's look at 2. Now this time we're given the two functions. We're going to determine graphically if they're inverses, but we have to graph them. You could plug it in the calculator, find the points from the table, but you could also, since these are linear, use slope and y-intercept. So that's what I'm going to do. So this first one, my slope would be 1/3. Y-intercept's 2. So it's crossing at 2 on the y-axis. And then we're going up 1, right 3. Up 1, right 3. I'm going to continue that throughout the graph as far as I can go, and then back down. Down 1, left 3. So there's that one. And then the second one, function g, slope would be 3/1, y-intercept would be -2. So this one's crossing the y at -2, and then we're going up 3, right 1, up 3, right 1. And then also let's go ahead and draw our reflection line, which is y equals x. Okay, so first thing you should notice is they do intersect. So remember I told you if they do intersect, it has to be on the intersection line. Notice it's a little above. Also, you can check your points. Let's just choose this one here. That's 0, -2, which means we should have a -2, 0 on the other side, and we do not. So these are not inverses. Okay, I'm just going to explain here. So because they do not intersect on y equals x, and points aren't flipped. Okay, so if they do intersect, remember it has to be on that line. If it's not on the line, we automatically know that it's not an inverse. So we know it's not reflected. Okay, so that's determining graphically if two functions are inverses. Now let's look at the back. Now we're going to talk about it algebraically. So it says if functions f and g are inverses of each other, then f of g of x, remember we've been talking about that, that's a composite function, so f composed with g, needs to equal x, and then g of f of x needs to equal x. So that if those are both equaling x, we know that those are inverses of each other. So on example 3, that's what we're going to do, determine algebraically if they're inverses. So I'm going to start out with function f. F of x equals 2x plus 1, or 2x plus 4. And then g of x equals 1/2 x minus 2. So I'm going to start out with doing f of g of x. Remember on composite functions, that's on 1, 1. The inside is your input. So notice my function g is inside. So I'm going to rewrite this as f of g of x, which is 1/2 x minus 2. So I'm going to input that into x for function f. So I'm going to have 2 times, in place of x, we're putting 1/2 x minus 2. And then notice we have the plus 4. So I'm going to distribute. 2 times 1/2 x is just 1x. 2 times a negative 2 is a negative 4. And then we have that plus 4. Notice negative 4 plus 4 is going to cancel out, and we're just going to be left with an x. So we now know f of g of x equals x, which is what we want it to equal. Now we need to check g of f of x. So I'm going to do g of f of x. So my input this time is going to be my function f, which is 2x plus 4. So I'm going to rewrite this as g of (2x plus 4). So I'm replacing x with 2x plus 4 on function g. So I should have 1/2 in place of x. I'm putting 2x plus 4. And then notice on function g we're subtracting 2. So I need to distribute. So 1/2 times 2x is just a 1x. 1/2 times 4 is 2. Minus 2, notice those cancel. So you're left with x. So both of those equal x. So therefore, they would be inverses of each other. So that's one way algebraically to determine if two functions are inverses. F of g of x and g of f of x both need to equal x. All right, the last two, it says determine both algebraically and graphically whether or not f and g are inverse functions. So I'm going to start with algebraically on both of these. So f of x is 4x plus 3. G of x is 1/4 x minus 3. So I'm going to start out with f of g of x. So my input would be g of x, which is 1/4 x minus 3. So I'm going to replace x with 1/4 x minus 3 into function f. So 4 parentheses in place of x, 1/4 x minus 3. And then notice you have a plus 3 after. So I'm going to distribute. 4 times 1/4 x is just a 1x. 4 times a negative 3 is a negative 12 plus 3, which does not equal x because the negative 12 and 3 did not cancel out. Okay, so now I'm going to go ahead and plug in or find g of f of x just in case I made a mistake on this one. So I'm going to do g of f of x. So my input is f of x. So I'm going to have g f of x is 4x plus 3. So in function g, 1/4. In place of x, I'm putting 4x plus 3. And then I have a minus 3. So I'm going to distribute. So 1/4 times 4x is just a 1x. 1/4 times 3, we're going to get 3/4 minus 3, which is not going to give us an x. So neither of those equal x, which means they're not inverses of each other. I'm going to write no here, but the instructions said show both algebraically and graphically. So let's see what it would look like on the graph. So function f, since these are both linear, I'm going to use slope and y-intercept, but again, you can plug it in the calculator and find those points. So it crosses the y at 3, and you're going up 4, right 1. And then function g crosses y at negative 3, and we're going up 1, right 3. My bad, up 1, right 4. I'm going to draw my line y equals x. Now on these, since you're looking at where they're intersecting, if it's on that y equals x line, you need to actually draw those points out so you can be accurate. Okay, so look at it. Notice they do intersect. It's not on the line, so we automatically know that these would not be inverses. Also, you could check the points, see if they flip. If they don't flip, we know that they're not inverses. So that's how we can show algebraically and graphically. All right, last one. So function f is 3x plus 6. Function g is 1/3 x minus 2. So I'm going to start off algebraically. I'm going to find f of g of x. So my input is going to be my function g, which is 1/3 x minus 2. So I have function f, 3 times x, which we're replacing 1/3 x minus 2. And then we have the plus 6, because we're looking at that function there. So when we distribute, we're going to get 1x minus 6 plus 6, which those cancel, so it equals x. Then finding g of f of x. I'm going to input function f, which is 3x plus 6 into function g. So I have 1/3 times 3x plus 6 and then minus 2. So when we distribute, we get x. 1/3 times 6, we'll get 6 over 3, which equals 2, minus 2, which those cancel, and that equals x. So both of these equal x, which means they would be inverses. But again, on these two, it asks to show algebraically and graphically. So let's look at function f. These are both linear, so I'm going to use slope and y-intercept. You could also plug it in the calculator. It's crossing the y at 6, up 3, right 1, down 3, left 1, and then function g crosses the y at -2 and going up 1, right 3. And then drawing my y equals x line. Notice they do intersect on the line y equals x. You could also check your points, make sure that they're flipped. So this would be a function. So this is how you can determine algebraically if you're given two functions if they're inverses. So algebraically and then graphically.